All right, here we go. So, round one of revision. So we're going to go over the chapter 1 content, which I've put here as 0, introductory concepts. And so in here we've got exponential functions, we've got logarithms, and we've got trigonometric functions. Now, when we've assessed this, and this is for the past 7-8 years that I've taught the course, the way I've done it is we've tested all of these skills across all of the tests. Okay? There are some other ways of performing the course. For instance, some schools will have a test specifically on exponentials and logarithms. Okay? And then those won't be assessed in any other units. I think it makes sense to do it across all of them because they do pop up in stats, they do pop up in calculus, and they do pop up in integration. So that's why they're sort of introductory concepts, they're skills that we're using across all of the units that we've done. So just to start with, let's just talk about what this statement means. If I have e to the x is greater than 0, in fact, it's the case for any exponential function. And an exponential function is a function where the base is a number and the power is the variable, right? And they tend to have this kind of shape, okay? That's the basic exponential function, but we can transform it and so forth, which means we can shift it downwards, but the basic exponential function is always positive, it's above the x-axis, it has an asymptote, all right? It doesn't matter how far you go negative, you're never going to reach 0, okay? It's infinitely close to it. So that's all we're saying with the first point. Then into logarithms, okay? So I'm going to keep that up here to contrast that when we talk about logarithmic functions, but here we've just got simplify the following logarithms. Now with these, you can type them into your calculator, right? But I think it makes sense for us to understand how they're going to simplify and so forth. This logarithm here is in base 10, which means we need to express this as a single power of 10 using index laws. So feel free to follow along with me and write them down and so forth. There should be enough room there for you to do them. So that's our first step, is to express it as 10 times 10 to the half. All right, now 10 by itself is even 10 to the power of 1. So you can think of those powers. We're going to add those powers together. 1 plus a half is 1.5, or 3 on 2 as a fraction. And now that we've expressed this as a single power of 10, it simplifies to the power. Okay, so log of 10 root 10 is 3 on top of 2. All right, we have ln of 1 on e. Now, what we need to do here is express, because it's the logarithm in base e, express it as a single power of e. We can take it to the top of the fraction as long as we make the power negative. Yeah? So at the moment, there's a positive power of 1 there. We're taking it to the top and making the power negative. This 1, it's still technically here, but 1 times e is the same as e to the minus 1. So we don't need to write it. We've expressed it as a single power of e, so it simplifies to minus 1. Okay, so not only can we simplify logarithms, but we can collect them as well. We've got 3 ln 2 take away ln 4. So, what we have to do here, you might remember, if I flick over the page and have a look at this box, second from the top on the right. We've got the 3 rules for collecting logarithms. They apply for logarithms in base, or in any base, okay, as long as the base is the same. So here we have the logarithms in both base e. So we're going to use the last rule first. We need to take that power to the top. It's ln 2 to the 3, which becomes ln of 8. Okay, then we've got ln of 8, take ln of 4. We can write it as ln of 8 on top of 4, which is ln of 2. Alright, so they pop up a bit in exams using these rules and using them in a way to either simplify calculus you have to perform or to discover relationships between certain functions. Okay, then let's move on to D, and here we've got an exponential equation, and we can solve this either by equating the bases or by doing logarithms. Let's use both processes just to revise both processes. So if we're going to equate the bases, here we have a base of 3. I need to express this number as a base of 3 as well. So we'll have 3 squared. And now because the base is the same on both sides, the power also has to be the same. So we would have x take 2 equals 2. We're going to plus 2 to both sides. X is 4. Okay, so that's a very easy way to solve it, right? Using, by equating the bases. Let's look at how we would use logarithms to solve it. I said I was going to leave that up. So we're going to start with this statement again. We've got 3 to the x take 2 equals 9. So when we're solving a logarithmic equation, solving an exponential equation using logarithms, we need to make sure we've only got the base left over. Then we're going to log both sides. Right? Doesn't matter if we log base 10, doesn't matter if we log base e. We tend to stick with base e in this course. All right, so I'm performing the logarithm of both sides, and now I can pull that power out the front, right? So we'll have x take 2 times ln 3 equals ln 9. And then we're just breaking it down to get x by itself. Okay, divide both sides by ln 3. And then plus 2 to both sides. All right, now you'd be fine to leave your answer like that. It's technically correct. Put it in your calculator, that's what you'll get. But I'll show you how we can get there as well. Let's just focus on this part, ln 9 on ln 3. Okay, this is the same as ln 3 squared on ln 3, which is the same as 2 ln 3 on ln 3. We have ln 3 at the top and ln 3 at the bottom. So this simplifies to 2, doesn't it? All right, and so you have 2 plus 2, you have 4. All right, so just showing you how we can use the equating the bases process, provided they have a base in common. Otherwise, we have to use logarithms. The only reason this answer's come out so neat is because they did have a base in common. All right, any questions so far? Hopefully we're pretty okay with most of these skills. Let's move on then to the discussion of logarithmic functions. And we see logarithmic functions exist for x is greater than 0. And so have a look. Exponential functions exist for, I think, y is greater than 0, okay, because we have y equals e to the x. And logarithmic functions exist for x is greater than 0. And that's because they're the inverse of one another, right? So I actually am going to sketch it again. Remember, if this is an exponential function, then this is the logarithmic function, that they're the mirror reflection about the line y equals x. So if exponential functions have an asymptote on the x-axis, then logarithmic functions have an asymptote on the y-axis, which means ln of 0 doesn't exist, right? ln of negative numbers doesn't exist. It has to be a positive number in here. Okay, excellent. So that's 1c. Let's move on to 1d. Unless there's any questions, interrupt at any stage. Very good. So on to trig functions. Now we've got sine 2x equals half. So we've got a trigonometric equation and we're going to solve it using the unit circle. We're not given a constraint here, which means we're going to find every possible solution that makes this true, right? So we're going to investigate one rotation and then add a statement that justifies every possible rotation. So if we're investigating one rotation, this is what it would be, right? Between 0 and 2 pi. However, in here we have a product of 2. So that means we need to double the domain. We multiply all of that by 2. So within one rotation of the unit circle, there's potentially 4 answers. All right? So then what we're doing is we're going, okay, what are the values of theta? What are the values of the angle that make the sine value half? So on the unit circle, sine is the y values. All right, y is sine of theta. And we want to know when the y values are half. So it's going to occur here and here. They're the two values where y is half. So on the first rotation, they're going to be pi on 6 and 5 pi on 6. You can see them on your unit circle, okay? So we've got the unit circle on the page over there. we've got the y value. Where is the y coordinate positive half? Pi on 6 and 5 pi on 6. So they are the answers within the first rotation, okay? But our domain extends to 4 pi because of this 2 out the front. Our domain extends to 4 pi, which means we need to go past them again. So our answers are pi on 6, 5 pi on 6, pi on 6 plus 2 pi, and 5 pi on 6 plus 2 pi. Okay, they're our answers within one wavelength. Okay, so then what we do, we can collect those. You can do it in your calculator, you can perform the fraction operations. I'll just simplify them first. We've got pi on 6, 5 pi on 6, we'll have 13 pi on 6, and 17 pi on 6. Okay, then what we'll do, we've got, this is what 2x is equal to. So we're going to divide both sides by 2, which gives us pi on 12, 5 pi on 12, 13 pi on 12, 17 pi on 12. Okay, so there's a couple of ways of answering this, right? And probably, I don't think I've done the most direct way, but what we've done is absolutely fine. I'll point out what's going on with these solutions in a moment. The only other thing we need to add, all right, is plus k2 pi for all k is an integer. Okay, plus k2 pi for all k is an integer. And what that allows, so these are the solutions we've got within a wavelength. And then this says going forward infinity and going backwards infinity. All right, so plus multiples of 2 pi, where the multiple has to be an integer multiple. It's a whole number. So let me explain then. So this is correct. There is an alternative way to answer it. If you think of the sine function, this is what it looks like. Now, because that's sine of x, because we have sine of 2x, what it means is there are 2 wavelengths in 2 pi, right? So that means it looks more, this function looks more like this, okay? And so the solutions that we've found when is it equal to half? We found here, that's the pi on 6, the 5 pi on 6. I might write this one out so you guys don't be confused by that. Pi on 6, 5 pi on 6, 13 pi on 6, 17 pi on 6. Okay, so that's where it's half. And then we've said plus multiples of 2 pi. So, 2 pi is here. So then we've got the next multiple of 2 pi and the next multiple of 2 pi and going back the other way as well. However, we didn't have to express it as a multiple of 2 pi. We could have just found these and expressed it as a multiple of pi, because that's pi units along, that's pi units along, the next one's pi units along. Both are correct. I think maybe this does make a bit more sense because you don't have to consider the domain of the function. Nonetheless, there's our answer. Okay. Any questions? Trigonometric functions. All right. So it might be a skill to have a bit more of a look at. I know in year 11, these are sort of 3-4 marks, and students find these challenging, and it's something we've sort of briefly gone over, but it is an important part of the course. Okay, very good. Let's move on then. We've got theta. Theta is 5 pi on 6. Find tan of 5 pi on 6. Okay, so the simplest way would be to put this into your calculator. Now, for your calculator, definitely radians unless otherwise stated. Okay, not degrees. I know you're doing physics, keep it in degrees, make sure it's in radians. Radians unless otherwise stated. So assume radians, that's a default assumption, right? If it's in degrees, it will say put it in degrees. So we have tan of 5 pi on 6, so you could just type that in your calculator and it's going to spit out an answer, okay? Let's think about how can we use the unit circle. Well, remember, tan of theta is sine divided by cos. So that's one of the trigonometric identities. And so what we've got then is tan of 5 pi on 6 is sine of 5 pi on 6 on top of cos of 5 pi on 6. All right, and then you can just have a look at your unit circle. 5 pi on 6, that's here. The sine value is positive half. The cos value is negative root 3 on 2. You can put it in your calculator. You can do your AD on BC. We've got negative 1 on root 3. Okay, find the equation of this trig function. That's enough. All right, so the basic, this is a sine function, and you'd be told sine function if you so forth, but the basic sine function has these properties, okay? A is the amplitude, that's the distance from the principal axis to a peak or a trough. That's the dilation factor, right? How much are we stretching it away from the x-axis? The vertical dilation factor. D is just translation. It's whatever the sine value is, and then plus D, move it up. Take D, move it down, okay? So that just shifts it up and down. And that's going to be the equation of the principal axis. Normally the principal axis is the x-axis. All right, normally it's just, if you don't have any value there, it's just 0. But now we can see the principal axis is here. We've shifted it up 1 unit. The value of D in this circumstance is positive 1. Okay, the value of A is the distance from the principal axis to a peak or to a trough. So we can see from 1 to 4, that's 3 units. And from 1 to minus 2, that's 3 units. So you can think of the amplitude like that. The other way you can think of it is the amplitude is half the distance from a peak to a trough, okay? So if we go from 4 to minus 2, that has a distance of 6. Half of 6 is 3. All right, sine, and then we have this bx, and the value of b just is how many wavelengths are there in 2 pi? And we can see we've got 1 wavelength in pi, 2 wavelengths in 2 pi. So that would be the equation of this function. All right, so let's flip the page then and we'll move over to calculus. So summary of the rules that you need here, and then we've only got a few questions to go through together. Simple differentiation, chain rule. All right. So we've got the first principles question. It's a nice, easy rinse and repeat one. Happy to go through that one, everyone? Or, yep, cool. So the first principles formula is this. All right, we've got 10 minutes, we can do it before recess. Okay, so that's the formula. They pop up in a few exams, not every exam, maybe 30-40% of exams you'll have a first principles one. Sometimes they're hard, sometimes they're easy. Like for instance, last year's exam, I think has a nice easy one, sort of 3 marks. So we've got the function x squared plus 2x. Okay, so let's put it in. F dash of x equals the limit as h approaches 0 of f of x plus h. Okay, so that means you're substituting x plus h everywhere there's an x. So f of x plus h. Take away f of x. Make sure f of x is in brackets because the negative needs to distribute. All on top of h. All right, we'll expand it out. So, once we've expanded it, perfect square expansion, distributive law, distributed the negative, I've just written everything as it is, and then we can start to cancel, right? We've got x squared take x squared, positive 2x take away 2x, and you notice everything we have left needs to have a h in it so that we can cancel it, right? Alright, so we can cancel the h. What we're effectively doing, factorising it and cancelling it, right? And so we're left with 2x plus h plus 2. H approaches 0, apply the limit, 2x plus 2. Okay, so make sure you keep your limit flowing until you apply it. And you can anticipate that answer using simple differentiation here, right? 2x plus 2, 2x plus 2. So you know the answer, you've got to work towards it, make sure you get it right. Okay, simple differentiation, that's where we're using this rule. If we have x to the power of n, the derivative is nx to the power of n take 1. So I've given you this equation. Three x plus 2x squared on top of x squared. Now here you could go ahead and use the quotient rule. It would take a long time to simplify it and so forth. Instead what we can do, because we have everything is just x at the top and the bottom, we can split that denominator, right? And we can use those index laws. So what we have is y equals 3x on x squared plus 2x squared on x squared. And now we simplify these. This becomes 3 on top of x plus 2. And I'll write it like this even, 3x to the minus 1 plus 2. And then we'll differentiate. So be very clear with your notation, okay? You don't just go equals, 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 equals. It's y equals, y equals, y equals, y equals, and then dy on dx equals, because that's where we're performing the differentiation. These are not equal to one another, okay? We've performed a process between here and here. We've differentiated the function. Okay, so that's simple differentiation. Let's do the chain rule. Chain rule says if we have a function to the power of n, then the derivative is n f of x n take 1 times f dash of x. Okay, that's the chain rule. So we've got x squared take 3x to the power of 5. Okay, so the function is x squared take 3x, the power is 5, so we're just going to follow this formula. It's going to become, let's use the correct notation. Y equals, so then dy on dx equals 5. X squared take 3x to the power of 4. N, f of x, n take 1, multiplied by f dash of x. Okay, we can see we've got a product rule and the quotient rule just stated there. So they're further rules that we use for differentiation. You can pull a couple out and have a go at them yourself. Move on to 2f, derivatives of exponentials. E to the f of x goes to f dash of x, e to the f of x. Alright, so we have 2e to the 3x plus 4, and y equals. So that number out the front, 2, that just hangs out there. It's a product. It's just going to stay there. It has no impact. So then we'll go dy on dx will be 2. All right? And we have e to the f of x. So we need to differentiate that power and put it down here as a product. 3x plus 4 goes to 3. All right? Notice how we've got e to the f of x goes to f dash of x e to the f of x. That 2 just hanging out the front. Alright, and still y dy of dx. Okay, ln of 2x squared take to the power of 3, take away 4. Now, whenever you've got the ln functions and you're differentiating them, always look for, can I simplify it using the log rules? All right, do I have ln of a on b, or do I have ln of a times b? Can I split them? Because that's going to save you using the product rule or equation. Here we can't. All right, we've got 2x to the 3 take 4. And so when you have a ln function, it goes from ln f of x to f dash of x on top of f of x. So here, f dash of x, when we differentiate this, we're going to have 6x squared at the top, and the f function at the bottom stays the same. So we got y again, y equals dy on dx equals. Okay, and last one, cos of 2x. Okay, cos of f of x goes to negative f dash of x sine of f of x. So when we differentiate cos of 2x, minus 2 sine of 2x. Okay, negative f dash of x sine of f of x. All right, just following rules alongside. All right, very good. So we got that done just in time for recess. I'll flick through the 2018 exam, and now that we've done chapter 1 and 2, I'll just point out the questions that we've done the skills for. And so that might be your first port of call. You might want to look at some review sets. You might want to look at some practice tests. You might want to look at the test that we did this year, see what are the things I didn't do quite right, what are some of the things I can have another go at. So basically, when we get back from recess, 40 minutes, see how you're going to direct your time.